The previous video introduced second-order differential linear equations that had constant coefficients that were non-homogeneous. So they didn't have 0 on the right-hand side, but instead had some forcing term. In the example of the mass on a spring, these are any additional forces on the mass besides the damping force and the spring itself. So we were examining this solutions to this differential equation. We learned that we could solve it using the linearity principles, but that required coming up with one particular solution, and to do that we talked about the method of undetermined coefficients, and that works in certain cases. Now we saw examples, or at least one example, of an exponential forcing term, a polynomial forcing term. Okay, but what we didn't do an example of, but I said it was still possible, was a sine or a cosine forcing term. And in this video I want to look at that because there's something slightly special we can do. It's a slightly different approach that makes things go a little bit easier to do the method of undetermined coefficients when you have a sine or a cosine. So this is called sinusoidal forcing. Sinusoidal is the adjective we use for either a sine or a cosine type function. They're both considered sinusoidal. Yeah, so we want to see what special approach we can use when we have a sine or a cosine on the right-hand side. Before getting into the details, let me just say that sinusoidal forcing has important applications. So anything that vibrates can be thought of as a sinusoidal force. Something that shakes back and forth is essentially applying an oscillatory or sinusoidal type force to whatever it's shaking at. So an example could be an earthquake tremor. So an earthquake tremor is a back and forth motion that would apply a force to, for example, a building or something like that. Sound, of course, we don't think of it outside of our science classes as oscillatory motion, but that's what it is. Sound waves are air molecules moving back and forth, and that propagates through the air and will hit objects and shake them. So sound can be a sinusoidal force on an object. And we're going to talk about, for example, we've all seen examples or videos of a crystal glass, and when the opera singer hits just the right note, the glass shatters. So that's because just the right kind of sinusoidal force is being applied to the glass. Now you might say, well, I thought we were talking about a mass on a spring. Well, these aren't masses on springs, but the glass, for example, responds to the vibrating by vibrating itself. And the glass vibrating back and forth is sort of like a spring a mass on a spring. And so it would follow this kind of left-hand side of the differential equation. So yeah, the applications are widespread for this kind of a thing. Now for the approach that we're going to use, I want to remind you of something you would have learned in a previous class, maybe a Calc 2 class or a complex numbers class, and that's Euler's formula. And it has to do with the fact that all complex numbers can be written in a polar or exponential form. But I won't go over that whole set of material. I just want to remind you of the formula itself. And it says that e to an imaginary number, so a multiple of I, and whatever the multiple is I'm representing here as theta. So e to like 5i, or e to the negative 2i power. You can break that down into a real part and an imaginary part, and the real and imaginary parts are cosine and sine of that number. So for example, e to the 3i, theta would be 3 here, that'd be cosine 3 plus I times sine 3. Okay, so we're breaking it down in sort of the standard way of writing complex numbers, blank plus blank I, right? Okay, so Euler's formula is going to be really key in what we're about to do. So we'll bring that in when we need it. Let's take a look at this example. So we'll explain the technique using this example. So this is second order constant coefficient linear, but it's non-homogeneous, and we have this sinusoidal forcing term. We have a sine 2t over here with a coefficient in front. So remember that the basic approach here is that our general solution will be at one particular solution to this actual differential equation plus the solution to the corresponding homogeneous. Now let me get the homogeneous one out of the way. That part's going to be the same, because of course that means we put a 0 here, right? So we rewrite the differential equation with a 0 on the right. We go to solve it, switching to our characteristic equation. We solve this quadratic formula. This is the square root of negative 64, which is 8i. So I think we will get negative 2 plus or minus 4i. All right, so the homogeneous part will be a e to the minus 2t cosine 4t plus b e to the minus 2t sine 4t. So that's all the same, and that's all well and good. We got this guy done, taken care of. But now, the particular solution, and this is the method of undetermined coefficients. So rather than doing what we did in the previous video, which would be to make a kind of the obvious guess here, maybe like d cosine 2t plus e sine 2t, you can get that to work, and that would all be fine. But I'm going to show you a different approach that makes use of exponentials and complex numbers. And I know that seems like we're making things a lot harder, but if you're comfortable with, if you get to be comfortable with that stuff, then this approach will be quicker. And A, I would like you to know this quicker way, but B, I would also like you to get more comfortable with exponentials and complex numbers. All right, so let me show you how this works. Okay, so here's the differential equation. We want to find one particular solution, our yp. And what we're going to do, it's called complexification. We are going to complexify this. So here's what I mean by that. On the right, instead of minus 3 sine 2t, I'm going to put minus 3 e to the 2ti. Now, based on Euler's formula that we just talked about, e to the 2ti, right? E to the 2ti is cosine 2t plus I sine 2t. And if I put a minus 3 on the outside, I'll have this. So you see that my original right-hand side is the imaginary part of this guy. So this is the imaginary part of this. So I've replaced this guy with a complex number that has this as its imaginary number. It has this cosine as its real part. Okay. And now the thought process is, if I can solve the complexified version, well, the imaginary part of that solution will be the answer to my original. Okay, so that's going to be our approach. We're going to solve this guy, and we're going to benefit from the fact that it's an exponential, you'll see, and that's where the speed up in time happens. These are easier when they're exponentials. We'll solve this, And then we'll just have the one additional step of then taking the imaginary part of that, and that will be the solution to our original. Okay, and I hope that makes sense. You can, officially prove that what I just wrote down here is true. That because this is the imaginary part of that the solutions will sort of have the same relationship. It can be proved. It's in our textbooks. I won't show you that, but hopefully it doesn't sound too crazy. Okay, so here we go. So now we have an exponential here. That's better because all we have to do now is we would guess that our particular solution is d e to the 2ti. Right? And here's why it's faster. It's not faster when I'm explaining everything in great detail the first time, but once you sort of know what's going on and you just do this from beginning to end, it is faster. Right? The normal approach to our original would have had us guess a d cosine 2t plus e sine 2t. We had to have had two terms there, right? And that would have meant two undetermined coefficients, d and e, and then we would have had to solve, the algebra would have been solving two equations simultaneously. All right, not a big deal, but takes a little bit longer. Here we are going to have just one undetermined coefficient. It'll be a real easy algebra problem when we get to that point. So that's where the increase in efficiency happens. All right, so let's do our thing, right? So we need to plug this in here, here, and here, which means we need our first derivative and our second derivative. So now 2i, right? So taking the derivative with respect to t, so a 2i will drop down. And the second derivative, another 2i will drop down. We do have to remember that I squared is -1, so we get a -4d e to the 2ti. All right, now we plug everything in. So we get -4d e to the 2ti plus, and then it was 4 times the first derivative, so that'll be 8i d e to the 2ti, and then plus 20 times y, so 20d e to the 2ti, and this is supposed to equal -3 e to the 2ti. Now it's all e to the 2ti, right? So that all just factors together. In fact, all three of these terms have an e to the 2ti and a d. So I can factor out the d and the e to the 2ti, and I'm left with -4, 8i, and 20. The -4 and the 20 are 16 plus 8i. And on the other side we have -3 e to the 2ti. Okay, so the e to the 2ti's are the same on both sides. And so it looks like d is going to be -3 divided by 16 plus 8i. And so you see the algebra was very simple. We didn't have to solve for two different variables and use some sort of either linear algebra or method of elimination or something like that. We just simply divided. Now, one small matter is that this is a complex number, right? And we're dividing by something that involves I. So usually what we do at this point, and you may remember this, how do we divide by a complex number? We simplify this. The trick was always to multiply by the conjugate. The complex conjugate of 16 plus 8i is 16 minus 8i. You make the imaginary part opposite sign. Now when you multiply that out, let's see, on the top we'll get -48 plus 24i. And on the bottom, the reason this little trick works, right, is because you'll have 16 times a -8i and an 8i times a 16 positive. Those will cancel. So the I part goes away in the bottom. You will be left with a 16 times a 16 and an 8i times a -8i, which is 16 squared, and 8i times a -8i will actually be plus 8 squared. And I think I'm getting 320. that bottom calculation will always just be the two numbers you have squared added together, sort of an a squared plus b squared kind of calculation. Okay, and so that gives us negative 3/20 plus 3/40 I. So there is my undetermined coefficient, and it's a complex number. So back to my guess, right? My guess was that it was some number times e to the 2ti. I now have the d. So my guess was negative 3/20 plus 3/40 I e to the 2ti. And that is my particular solution to the complexified differential equation. Now, as we said, what we do now is we take the imaginary part of that, and that is guaranteed to be a solution to our problem. So, we take the imaginary part of this, and here's how we do that, and it's not too hard. Once again, well, here, let me copy this part down. Once again, we remember Euler's formula. This is cosine of 2t plus I sine of 2t. Okay, so when we multiply this out, that times that, negative 3/20 cosine of 2t. And let me see, the two I pieces, right? I times I is negative 1, so that'll be minus 3/40 sine of 2t. I'm foiling this out, and those are I just did the two that will give me non-I pieces. And now I'll do the I pieces. That'll be this one, right? So that's minus 3/20 sine of 2t. And this one, which is 3/40 cosine of 2t. And remember, we're supposed to take the imaginary part, so that's the part that's on the I. So our yp is negative 3/20 sine 2t plus 3/40 cosine of 2t. And that's the answer. And again, when you have somebody stepping through it and explaining every little step in a first example, it maybe doesn't seem too quick, but it actually it is. It's faster, and it's also worth just getting acquainted or reacquainted with complex exponentials, and that's maybe as important a reason for covering it this way. Now, just to finish this off, then, that's our particular solution. Remember, our homogeneous solution was right here, and so we would put it all together. So I've copied them both in the same place. So our final answer would be y equals negative 3/20 sine of 2t plus 3/40 cosine of 2t plus arbitrary constant a e to the minus 2t cosine 4t plus arbitrary constant b e to the minus 2t sine 4t. And as usual, if we had initial conditions, we would now apply them, and we could solve for a and b. Just a quick word about this solution that we have found. The homogeneous part is an e to the minus 2t in both terms. We could, of course, factor that out if we wanted to. That is a negative exponential. This part decays exponentially to 0, right? So even though the initial conditions are what are going to tell us what a and b are, it turns out that part of the formula kind of goes away pretty quickly anyway. And so this is sort of what's left over. So as with the first, I think this is the first time I'm saying it for a second order solution, but it's the same idea as with first order. This is what we call the steady state solution. This oscillating piece is what's going to persist. This is just sort of, because of where we started, this is just noise that's going to go away after a while, and we're going to be left with the steady state solution. Okay, so that's an example of how to do method of undetermined coefficients when you have sinusoidal forcing. And it's a technique that's worth knowing. Let me just say, go back to the beginning, or yeah, the beginning of the complexification part. We had a sine, right? So we replaced the sine with the corresponding exponential, and we said that the sine was the imaginary part of the exponential. So just to be clear, if we had a cosine here, right, a cosine, then it would have been the real part. Our differential equation would have been the real part of this differential equation. So when we got all the way down to the end, rather than taking the imaginary part as we did, we would have taken the real part. In fact, we got that solution. We've done all the work for that. That would be the particular solution to the differential equation that was minus 3 cosine 2t. Okay, so for sine, that's the imaginary part. For cosine, that's the real part.